Section 1.9 is on power functions and their graphs. A power function is of the form f of x equals x to the n, where n is a whole number or positive integer. And in this case, n is the degree of the power function. First, we want to take a look at what some graphs of power functions look like for positive integers. So you grab your calculator, you can graph a couple functions like f of x equals x squared. You may already know what that shape looks like. And then you can graph a few other power functions where they're going to have just different integers. So how about x cubed? And if you use your calculator, you can get a sketch for this graph. Looks approximately like this. And f of x equals x to the fourth. I encourage you to try this on your calculator to see what they look like. In particular, on your calculator, you might note a difference between the two functions that I graphed here for x squared and x to the fourth. They are very similar, but you may notice that the x to the fourth graph is a little bit wider near the origin, but the shapes are going to be in general the same. And then if I look at just one or two more here, if we look at the graph of x to the fifth and use the calculator on that, you're going to see that the shape is very similar to that of x to the fifth, but it might be a little wider there around the origin again. Okay. So if we did this in class, you probably would have a chance to explore those shapes. Now, on the next page, we are looking at some transformations of graphs. We already saw these transformations when we did quadratics. And so we're going to look at the specific transformation for the power function. We're looking at the A transformation first. So in a power function, this would look like, there we go. This would look like f of x equals a times x to the n. And we mentioned when we did quadratics that the a was the narrowing or the widening of the graph. So we're going to have two cases here. We're going to have if a is greater than 1, our graph is going to look narrower. And if a is between 0 and 1, our graph is going to appear wider. So a's effect will depend on how large the a value is. Then the next transformation is the negative coefficient. So in terms of the power function, this would be negative x to the n. And just like with quadratics, that's going to be a reflection across the x-axis. Okay. Changes the y values to negative, so it flips them from the top down to the bottom, reflection across the x-axis. Then we have our h and k shifts. And if you remember from quadratics, when I had plus h versus minus h, what was the difference on that? There was a left-right. So in terms of the power function, it would look like that's an inside shift, so it's going to be x plus h to the nth power. Or if it's a minus shift, it would be the x minus h to the nth power. Now if you remember from our quadratics, the plus h was a left shift, and the minus h was a right shift. So those are kind of opposite of what we would expect necessarily in the inside right there. When we see that plus, we think right, perhaps, but it really does mean left. Oops. Then when we get back to our k's, they are what we would expect for our up-down shifts. Plus k is up, down k is the negative. And so these ones are after the end, so we have our x to the n plus k, and we have our x to the n minus k. Plus k is our up k units, and minus k is our down k units. All right. So just kind of grouping these together. Those two are both horizontal shifts. The bottom two are both vertical shifts. And then the top two are both coefficients, but there's a difference between if the coefficient is numeric versus if it's a sign negative. You can have a combination of those two things. A negative number is going to do both of those two things. All right. So those are the same basic transformations as we saw with the quadratics. Nothing different about those. We're just going to see how those apply to our power functions. Okay, first of all, we're looking at a power function, negative 2 times x to the fifth. I already know what x to the fifth looks like. Then I have a reflection. So down here in the basic shape, I already know that the basic shape for x to the fifth, again, if we saw on that previous page, we might not have made the connection yet, but we saw that we had one basic shape for the even degrees and another basic shape for the odd degrees. So we're going to use that basic shape. The evens were that more parabolic type shape, and the odds were more of that all increasing shape where they're swishing through the origin like that. Okay, and again, even, what I'm talking about for even right there is those powers, 2 and 4. And odd, we're talking about those powers, 3 and 5. All right, so on the next page, where we see that first box, that transformation box saying basic shape, I know that the basic shape with an odd power means that it's going to be all increasing, swish to the origin like this. But I do have two transformations. The transformations from the negative are reflected, and from the 2, it's going to be narrow. So now what I'm expecting is that the shape is going to look more like this. It's been reflected across the x-axis. This tail that was down is now up, and vice versa. Okay, and I've also kind of made it a little narrower as I drew it. We're going to sketch that a little more precisely here in a moment, but first we can do our domain and our range. This is a polynomial, and for any polynomial, negative infinity to infinity is going to be our domain. We can see that we're going to stretch across all the x's, both negative and positive. Range, any of the odd ones goes all the way up and all the way down for y, so the range for any odd is also going to be negative infinity to infinity. Okay, so we always, for polynomials, get negative infinity to infinity for the domain, and always for any odd, we get negative infinity to infinity for the range, because they'll be going up and down without bound. Not true of the evens, but is true of the odds. Okay, now, to actually get into the graph, we'll make a few ordered pairs right here. I don't have any left, right, up, down shifts, so my first ordered pair can be 0, 0, and if you plug in 0 for x, you see that you do get 0. And then I can plug in 1 and negative 1. If I plug in 1, 1 to the fifth is 1, times negative 2 is negative 2. And when I plug in negative 1 to the fifth is negative 1, times negative 2, we'll make that a positive 2. So I'm going to have 1, negative 2, and then negative 1, positive 2. I'm going to run out of points real fast. See what happens if I try plugging in 2. 2 to the fifth power is 32, times negative 2 is negative 64. So super, super low. But what that tells me is that I have to make my graph so narrow here that it doesn't go through, even really get close to that line where x is equal to 2 or negative 2, because it can't touch that line until you're down at negative 64. So it's a very, very steep graph. Having a couple ordered pairs helps me make sure I get the steepness correct. All right. Let's do the same thing in the next one. We're going to use transformations, and we're going to graph this. All right, this is also odd. I can see that that power right there is 3, so I have odd, which means that my basic shape is going to look like this, but I have some transformations. There's just one transformation on this one. It's that k value plus 5, so the transformation is up 5. So just a quick sketch over here. If I shift this up 5, now my graph should have that shape. The same shape right here, but just pushed up 5. Okay? And the domain and range are freebies because you have an odd power function. You're going to have tails up, tails down, both directions, so you're going to get negative infinity to infinity for both of those. Let's go back and get a few ordered pairs, and then we can have our graph. Okay, so 0, up 5, shifts this up 5, so 0, 5. And then we'll plug in 1 and negative 1. So when I plug in 1, 1 plus 5 is 6, negative 1 to the third is still negative 1, plus 5 is 4. There is symmetry there, as you noticed. You either change from that 5 value by the same amount, so we went up 1 and down 1. Over here, we change from that 0 value by going down 2 or up 2. So again, there is some symmetry there. Okay, so at 1, we're at 6, and at negative 1, we're at 4. We can try one more. If I plug in 2, 2 cubed is 8, and then 8 plus 5 is 13. It doesn't really fit. You could kind of dot out where it might be. Negative 2 I think will fit though, because it's got more room down here. Negative 2 to the fifth is negative 8. Negative 8 plus 5 is negative 3. So I can graph that one in. And again, we'll make our graph narrow. You may try, oops, little squiggly there, but you may want to try plugging in negative 3. I don't think it's going to fit on the graph. So we're going to make sure we're narrow enough not to go through it. Okay. Now, just noting the fact that this looks pretty narrow. It's not narrow for a cubic function. It's just because it's a cubic function that it does seem narrow. Notice that the fifth degree function is even narrower than the cubic. A higher order power will always be narrower. Right. And our last page. Two more functions we want to graph by transformations. These two both have even degree. So this one is degree 4. So since it's even, I'm expecting the basic shape to be more of that parabolic type, but there are some transformations. This one has two transformations. First is going to be reflected, and then that minus 3 on the inside, inner is opposite, so it's going to be right 3. Okay, so if I took this graph, moved it right 3, put 3 right there, and then reflected it, that's the shape I would expect to see. So we're hoping that our final answer is going to look like this. Now, domain and range. The domain for any polynomial function, power functions included, is negative infinity to infinity. You can plug any x value in. But the range depends. The range is going to go down all the way in this picture. We can figure out what's happening to the range. It goes down all the way, but it definitely has a upper limit, a cutoff value right here. So we're going to go down to negative infinity, up to 0 is that y value, include it. If there was an up-down shift, I would have that reflected here have that accounted for here. But there's no up-down shift, so I'm going to stay at 0. Let's plug in a few ordered pairs and get our graph. Oops, x, f of x. 0. Actually, before I shouldn't actually choose 0 first. I need to look at this. I get a right 3 shift, which means 3 should be the first x value I choose. Okay, so 3 into my function. 3 minus 3 is 0. 0 times negative 1 is still 0. So 3, 0. If I have a left or right shift, I want to start there. Okay, so the next point, I'm going to choose around there. I have 2 and 4. So if I choose 2 or 4, just a second. Let's plug in 4. 4 minus 1, or 4 minus 3, I meant to say, is 1. To the 4th power is 1. Times negative 1 is negative 1. The same is true for 2. 2 minus 3 is negative 1. To the 4th power is positive 1. Times negative 1 is negative 1. The symmetry should work on the even so that you have the exact same value for the values that are one space away on either side. So I'm at negative 1, negative 1. I need to go at least one more point just to find out how narrow this needs to be. So let's just plug in 5. 5 minus 3 is 2. To the 4th power is 16. Times negative 1 is negative 16. It's not going to fit, but it just helps me make sure that my graph is narrow enough, that I don't go through that negative 2 line until I was down at a value of negative 16. So this graph is really narrow, mostly because of the 4th power. Okay, so that's what this should look like. Okay, and the other one, basic shape, also even, which means that it's going to have that parabolic type shape. And so it has two transformations. Inner value of 4, opposite of the plus, so it's left 4. And then outer value of negative 2, so that's going to be down 2. Okay, so this would take that vertex from the middle, over left 4, down 2, and then I'm expecting a shape like this. All right, domain, always negative infinity to infinity. Range depends on your highest and lowest values. Okay, this went down 2, so it has a lowest value at negative 2. So I expect the range to be from negative 2 up to positive infinity. Those tails are going up, so infinity is the largest value. That downshift gave me a negative 2 as the smallest. Then we'll do some ordered pairs just to get things in the right places. Left 4, so negative 4 is going to be the first one. Plug in negative 4, you get 0 minus 2 is negative 2. We already moved over 4 and down 2, so we expect negative 4, 2 to be our first ordered pair, just from the transformations. And then either side of that, so we're going to plug in -5 and -3. If you plug in -3, -3 plus 4 is 1, to the 6 is 1, minus 2 is -1 on both of those. Again, symmetry. If you plug in -5, it's -1, to the 6 is positive, minus 2 is -1. So you expect that symmetry there on either side of your vertex. If I try plugging in one more value, say -2, -2 plus 4 is positive 2, to the 6th is 64, minus 2 is 62. Again, way too high to graph. So this is going to be very, very, very narrow. Okay. All right. Now, this graph didn't have a narrowing coefficient. It is narrower than the one down here because of the 6th power. The higher the power of the narrow it's going to be, regardless of any coefficient.